Calculus video 73, the mean value theorem and average value. Specifically here, we're talking about the mean value theorem for integrals and average value. We had a mean value theorem for derivatives earlier. Let's recall that just so we can keep them separate, and it's a good idea to kind of bring back these things to help us remember them. The mean value theorem for derivatives said this. Remember, derivatives is about the slope of the graph. If you had a function f here, I've drawn a curve f, on a particular interval a to b, and you took the average slope on a to b. So the average slope on a to b would be this point here. This is the point a f of a. And here is the point b f of b. The average slope would just be the slope that connects those two lines, a secant line there. That is the average slope. Average slope. The mean value theorem for derivatives said this. As long as that function is continuous on a to b, there exists a c somewhere between a and b. Let's let my c, looks like it's going to be about, say, right here. Not necessarily in the middle. This one kind of looks like it's in the middle, but it doesn't have to. I don't mean like exact middle. It's somewhere in between a and b. There's a c value somewhere between a and b such that the slope at c, and the average slope are the same. Okay? What that means is the slope at c, at a particular point c, that's given by the derivative, the rate of change of that curve at c, f prime of c. The average slope is given by f of b minus f of a over b minus a. And so the mean value theorem for derivatives said there's a c that exists such that f prime of c is equal to f of b minus f of a over b minus a. The slope at c is equal to the average slope. That's the mean value theorem for derivatives. What we want to do is do the mean value theorem for integrals. Same kind of similar idea, but now not with slope as for derivatives, but with integrals, we're going to look at the area under the curve. Okay? So the mean value theorem, or MVT for integrals, we're going to have some sort of a function here. I've drawn a function f on an interval a to b. And since we're talking about integrals now, we're going to be talking about the area under the curve. So the area under the curve from a to b looks like this. If I could draw straight lines, something like that, right? Some sort of area under the curve like that. What is the area under the curve? We should know that the area under the curve can be found by the integral, the definite integral from a to b of f of x dx. That gives us the exact area under the curve. Okay. The mean value theorem for integrals says this. We can create one rectangle, not lots of rectangles, just one rectangle that has the same area as the area under the curve along that same interval from a to b, as long as our function is continuous. So as long as our function is continuous from a to b, we can create one rectangle. Let's go with orange or green. We can create one rectangle that has the same width as our area under the curve, so the same sort of from a to b. If we make our rectangle of a certain height, let's say a height that looks kind of like, it's probably too high. Maybe even a little bit shorter. Maybe, nope, still too high. We'll go with that, even though it's probably still too high. Point being, we can create a rectangle that has the same area as the area under the curve. All right, so what's happening here is the rectangle is including this area here that the curve is not. The curve is including this area here that the rectangle is not. And all we have to do is, as long as that function is continuous, we just have to get the right height for the rectangle such that those two things are equal, such as those two areas in black and orange are equal. It looks like I probably needed to lower this just slightly, but you get the point. As long as the function is continuous on a to b, there will be a c within a to b such that the height at c, so here's my c, say right about here, the height at c, this point right here, that's f of c. That's the height of the rectangle. The width of the rectangle is just b minus a, right? The b minus a for the width there. That rectangle has the same area as the area under the curve. So area under the curve, integral from a to b of f of x dx, area of rectangle, base times height, base times height, that would be, I shouldn't use b, I already used b in this already. I'll just write out base times height. Which is equal to base b minus a times height, whatever the height is at f of c. And the mean value theorem for integrals says those two things are the same. You can create a rectangle that has the same area as the area under the curve. In other words, the mean value theorem for integrals says that there exists a c such that the area of the rectangle, b minus a times f of c, is equal to the area under the curve, the integral from a to b of f of x dx. The area of the rectangle, the area under the curve. A rectangle can be created so that the area of that rectangle is equal to the area under the curve. Okay, let's go ahead and write out the mean value theorem a little more mathematically here. Specifically, it says something like this: the mean value theorem for integrals. If f is continuous on the interval a to b, then there exists c. It probably should be there exists at least one c. It could actually happen multiple times. There exists at least one c in the interval a to b such that the area of the rectangle, b minus a times f of c, is equal to the area under the curve, the integral from a to b f of x dx. That is the mean value theorem for integrals. And that's great. But typically how we ask this question isn't just, okay, what is the mean value theorem for integrals? What we do is we often ask you, find that f of c. Find that particular height that creates the rectangle with the same area as the area under the curve. We will be asking you to find this f of c. And we call that f of c, we call that the average value. So if you see a problem that says find the average value, they're saying find the height of that rectangle so that the area of the rectangle is equal to the area under the curve. Find f of c, find the average value. Okay, well, you have this formula. You have the formula b minus a, I'll just rewrite it, b minus a times f of c is equal to the integral from a to b of f of x dx. If I asked you to find f of c, if I wanted you to solve for f of c, how would you solve for f of c? How would you get it all by itself? Well, hopefully you divide by b minus a. Okay, solving for f of c, we get the average value. That's f of c. That's equal to, divide both sides by b minus a, we'll write it like this, 1 divided by b minus a times the integral from a to b of f of x dx. That's how we find the average value. That's how we find the height of the rectangle. So I might give you a problem that looks something like this. So for example, find the average value of f of x equals 3 over x plus 1 on the interval 1 to 6. Find the average value of f of x equals 3 over x plus 1 on the interval 1 to 6. So 3 over x plus 1, that is a curve on the interval 1 to 6. 3 over x, if I'm just kind of freehand drawing, 3 over x would look like this. Add 1, it would kind of move up by 1, kind of like that. From 1 to 6, we get an area under the curve. And what I'm asking for is find the average value. Find that height f of c so that, that's probably too high. Maybe a little bit lower, maybe kind of right here. I'll go with that. So that the area of the rectangle is equal to the area under the curve. All right, so what is that f of c? What is that height? Well, f of c is equal to 1 over b minus a times the integral from a to b of f of x dx. That would be f of c is equal to 1 over 6 minus 1, that's b minus a, times the integral from 1 to 6 of 3 over x plus 1 dx. That's 1 over 5 times the integral from 1 to 6, 3 over x plus 1 dx. Okay, go ahead and do the integral here. Way back over here, that's 1 over 5 times 3 natural log absolute value of x, right? The integral of 3 over x is 3 natural log absolute value of x. The integral of 1 is x, evaluated from 1 to 6. We get 1/5 times, let's plug in the 6. 3 natural log 6 plus 6 minus, plug in the 1, 3 natural log 1 plus 1. That's 1/5. 3 natural log 6 plus 6. 3 natural log of 6, that's about 5.37, plus 6 should be 11.37, 11.38 maybe. Minus, all right, natural log of 1, we should know the natural log of 1 is 0, so that part's 0, so then it would just be minus 1. That's 1/5 times 10.38. Multiplying that out, I get about 2.08, 2.075, 2.08, somewhere about there. Okay. What that means is, on this particular curve, f of c would need a height of about 2.08 to have a rectangle with the same area as the area under the curve.